And today we're happy to have here in Zhuang to speaking about talk about solar energetic particles. He is here since 2019, working with solar energetic particles in the CME group with now Lucas. And here, all right, whenever you're ready.
Cool, thanks. Yeah. Okay. Good afternoon, everyone. I'm Zhuang, as just introduced. I joined the UH in 2019, so it has been more than 4 years. And I work with Noi and the CME group for these years. And here I'm very happy to share our recent studies about subatomic particles and quantum mass ejections, and also some future research plans that we are going to do in the future. And I would like to express my sincere appreciation to all collaborators, especially to Noi, for his great support and help during these years. And the presentation will contain 3 parts of the chapters. The first is about SEP studies using observations from multiple viewpoints and in multiple wavelengths. And the second part is about studying the CME radio expansion from the Coronal to interplanetary space. And then the final one is about our future research plans. So let's directly move to the first part, solar energetic particles. Here we focus on SEPs, like gradual and large SEP events. And as for those events, they are thought to be accelerated by shocks associated with fast and wide quantum mass ejection, as shown like this. And this middle movie shows a halo CME observed by white-type chronographs. And the right figure just shows the in situ SEP measurement associated with multiple CME eruptions. And as for SEP studies, there are many interesting and important aspects and points. So including acceleration, release, and the transport of particles, like from the sun to interplanetary space or to the heliosphere. And among those points, one importance is that understanding the CME-SEP relationship, as shown like in these 2 figures, like the CME parameters and SEP peak intensity. And of course, except the physical properties, SEPs also have very strong space weather effect. It will, of course, like for example, it will cause hazardous radiation exposure to astronauts, like shown like this mini figure here. So together, to investigate some energetic particles, we can use like advanced observational techniques, like for in situ measurements from multiple viewpoints, as shown like here. We have spacecraft distributed inside the heliosphere. And for example, the recently launched Solar Probe and Solar Opter. And then also to study the SEP driver quantum mass ejection, for example, we can use we can use remote sensing observations in multiple wavelengths from UV extreme ultraviolet to white light and then to radio wavelengths. So with these techniques, we first go to our first study, the twin CME scenario or twin CME scenario SEP event. And to explain the SEP CME relationship and also the generation of extremely large, intense SEP events, a twin CME scenario was proposed. And in this scenario, SEP particles are generated by this major CME. But prior to this major CME, there is this preceding CMEs. And that preceding CME can provide enhanced seed particle populations, and of course also the enhanced turbulence level, which is able for a more efficient particle acceleration for this major CME. And here we focus on studying the relationship between the acceleration and the release of SEPs and the CME-CME interaction, but we use remote sensing observations from multiple viewpoints. I want to emphasize here is that the multiple viewpoints remote sensing observations is very important because it will help reconstruct the CME-CME interaction in 3D space, and also help to identify the twin CME scenario. For example, like here, if you only have single viewpoint observation, it's hard to say that how these 2 CMEs will interact in 3D space. However, if you add 2 more viewpoints, it will become clear. So you can see that. And as for the particle release and acceleration, here, for the particle acceleration, we use radio observations And here it shows the type 2 radio burst along this line. This type 2 radio burst can indicate the generation of the CME-driven shock, which you can refer to the particle acceleration time. And as for the particle release, we use the velocity dispersion analysis. As for velocity dispersion, you know that if particles at different energies, they will arrive at a detector at different times. So we show a dispersion curve like this. And with these two information, particle acceleration time and the particle release time, combined with CME interaction in 3D space, we can get the relationship between the particle acceleration time, release time associated with different CME interaction types. And in solar cycle 24, we identify or found that there only exists 11 twin CME large SEP or just the SEP rich events. And this is a summary of such relationship between the interaction and the particle acceleration and the release. In this white, left-white region, it means that there is no CME interaction. And in the middle green region, it means the interaction is meaningful, means that the primary CME kept up with the preceding one. So the diamond here indicates the particle release time, and that left end means the particle acceleration time. So with this figure, we can see first, direct interaction is not necessary for the particle release, because we found some points here. And if we focus on these 5 data points, and it does say that meaningful interaction leads to a high SP peak intensity. So this is how we study this, interaction and SP acceleration and release, and then we use multiple observations. So here comes the first summary of this, this study. So it highlights the important role of using multiple viewpoint observations. And following this twin CME scenario, in causing SEP reach or causing large SEP events, we go to our second study. If we take an opposite consideration, that we can ask, do there exist twin CME but SEP pro events? Because you know that ultimately that the twin CME scenario will lead to a more efficient particle acceleration. So we would like to know whether there exists twin CME as a pure event, even the driver CME is fast and wide. If there exists, what are the reasons? And to do this, we found 19, of course, there exists twin CME as a pure events. We found 19 events during 2007 and 2014. And we also combined the past 11 twin CME SEP rich events. But at this time, we also use multiple spacecraft measurements from CLA, B, and L1 spacecrafts. It will show the longitudinal separation in the hemisphere. And this right figure just shows the longitudinal distribution of the SEP peak intensity observed by 3 spacecraft. And if you focus on these few symbols of one case, or also these featured curves, you can see the first thing is that magnetic connectivity is important for the SEP detection, in situ. So what's the meaning of magnetic connectivity? If at a in situ spacecraft, the particles will propagate along magnetic field lines. So if the particles attract particles back along the non-magnetic spiral line back to the sun, magnetic connectivity means the separation between the foot point of the spacecraft and the SEP source region. So first, magnetic connectivity is important, but this is not enough to explain the existence of the SEP pro events. Why? Because you do one, we can see some, even some cases are below this horizontal threshold. So we need to do more. And first, we try to do the one-on-one correlation between SEP peak intensity and of course combine multiple factors, which is related to the whole eruption processes, including the major CME speed, the solar flare size associated with eruption, and one important point is the seed particle duration measured. But here we only use particles measured near 1 AU, and of course the CME interaction that we studied previously. And then we do find some trend here, for example, this good CME speed SEP peak intensity relationship, but this is not enough because it's just one-on-one correlation. And due to the intrinsic relationship between different factors, because the CME, this eruption is a comprehensive process. So it will, like, all factors will be convolved together. So for example, like closed CME flat coupling. And the one-on-one correlation sometimes may not be convincing. So we, to overcome this problem, we use a statistical method called projection correlation. It has two advantages, and they are just suitable to solve this question. And this figure is a summary, like the correlation coefficient summary. We try the different combinations of like vectors, and we try to study the correlation, projection correlation between SEP and the different combinations. And the result here shows that first, the major CME speed, of course, based on this map, is still the major role, as most important role in controlling the SEP intensity. But we do find that, like, even after combining other factors, for example, the single particle population, the flat side, it won't improve the correlation coefficient compared to this pure CME speed. So then we need to do like to study more about this like close coupling relationship between inside the whole eruption. And yeah.
What would happen if you just carried out this analysis on the subset of events that have good magnetic connectivity, but poor,
That's a good point. So to do this for SEP peak intensity, we do consider magnetic connectivity first by two ways. First is that we use the spacecraft which shows the best magnetic connectivities with the SEP source region. We calculate the correlation coefficient. The second, we also use this fitted curve, use the peak. So it gives the similar results.
So, what energy and particle type are you looking at there?
Sorry.
What is the energy of the particles and the type of particles you're showing there?
This total and the energy, I think it should be here, like from between 15 and 40 MeV.
15 and 14 MeV.
Yeah.
Thank you.
Yeah. So, we use this, and then a summary here, quick summary here is that, we also do the study the twin CME SEP pro events, and we found that consideration of SEP pro events can help better understanding the CME SEP relationship, and we do find some reasons to explain. Yeah, please.
Yeah, do you have any examples of a single CME, so not a twin CME, but still has good or high flux intensities?
Yeah, there exists, of course. So for single CME, if the CME or like CME driven shock is strong enough, then of course it will lead to like very high intensity SEP events. So there exists. But here we focus on twin CME events because we follow in the previous logic that we thought twin CME will lead to even more efficient particle acceleration compared to single CMEs. Then we just say, okay, if the particle acceleration is more efficient, so we may expect like an SEP event with even higher intensity. Then we just say, okay, can we find SEP pro events if just within the twin CME scenario, like if the driver CME is still fast, and we do find that, and I want to know the reasons. And one reason is like magnetic connectivity, and one reason is also the CME speed.
How close do these CMEs have to be in space and time?
Oh, that's a good.
Before you consider them?
Yes. Let me go back to this one. Here, so that's twin CME scenario. It requires that the preceding CME should be the driver CME should be within like 12 hours after the preceding CME. So this is based on the calculation of the decay time of the circulating population and also the turbulence level. So first, the time interval between two CMEs, like it would be typically within 12 hours. The second is that how close the two CMEs will be. If you need that, like the preceding CME, you need that particles accelerated by the following CME, then the preceding CME should from the same active region or source region or from nearby source region if the two states are separated like by 180 degrees, then it won't contribute to anything there for the primary CME. So that's first 12 hours, second, the set are nearby source region. Okay, so and we do the correlation studies, and I would like to emphasize is that when combining like other factors, for example, the seed particle populations, but only measure the near one AO, it won't improve the correlation coefficients, which need further like investigation. Then here comes the third study, and we now go to the seed particle population here. And the seed particle populations are found to be very important in the shock accelerating mechanism. And the oranges of seed particle populations contain the lower energy portion of materials accelerated in preceding energetic particle events associated with qualitative interactions. The CME-driven shock, just like the twin theme scenario, sort of land and continuous acceleration processes in hyperspace. And then this figure shows the energy spectrum of particles, and the seed particle population energy range are found to be within this yellow range based on past studies. And we recall again the previous correlation study. As for these seed particle populations, we can always ask three questions, or many questions. The first is like how widely, and the second is how long the seed particle population can exist. And the third is like how seed particle population measured near one AO, as we have done previously, compared to those in the innermost hemisphere, because the particles are accelerated close to the sun, so we need the particles measured in the innermost hemisphere, that's very close to the acceleration site. And here, for example, we need measurements in the innermost hemisphere, for example, using particle solar probe. And this is particle solar probe. And for this study, we focus on 4 successive SEP events. And during this time, particle was at around 0.4 AU to 0.2 AU. And these 4 SEP events are generated or accelerated by multiple CM injections as of here. And this right figure just shows the SEP in situ measurement at particle and at stereo A. And here, stereo A and particle also should also observe the particle intensity enhancement. So considering the angular separation between stereo A and particle like here of around 100 degrees, it can answer the first question, how wide? And compare these like particle intensities measured at PSP and stereo A, we can see that the particle detects a much higher proton fluxes compared to that at stereo A, and that's also the same for different energies. And here, for example, like 1 to 2 MeV, we use it as an upper limitation of the seed particle population energy range. And yeah, here is just a comparison. And then we can just focus more, for example, on the decay time of these SEP events. This decay time or decay phase can answer the second question, how long? And this decay phase is also interesting to indicate the energetic particle reservoirs filling broad regions inside the hemisphere. And this is, again, of course, we use 1 to 2 MeV, and then we focus on this decay phase shaded by this shaded region. And using exponential fit, we can get decay time during these 4 SEP events, but at particle solar probe are found to be around 10 to 20 hours. Then this answer how long. And what about the decay phase at stereo A? Let's see this. Let's this sub-figure. You can see, or you may find that stereo A have a much longer decay time compared to that at particle solar probe. So what are the reasons? We thought it's due to the continuous injection by this CME when it propagates outward, and also due to the solar rotation, making the field lines close to stereo A. When the particles are transported due to the cross-field diffusion to both spacecraft. And yes, and then finally,
how much longer is it, the decay time at stereo?
it's more than like 100 hours, if just using the exponential fit. So this is around 15 hours, and then you can see this better plan.
And which one was better connected?
No,
Was Parker or stereo better connected?
no, they are quite far away, both spacecraft were quite far away from the active source region. So that's,
On the same side,
sorry,
on the same side.
no, not the sense that, like, the active source region is here. And let me show you this will be here. You can see this is the footprint of the Park solar probe. And this is like, that event is from this source region, then we use this one. So the angular separation between the footprint and SP source region is like, is around 100 degrees. So that will explain why the anisotropy observed by Park and Stereo are very low. Because they have poor connectivity to both spacecraft.
Is that magnetic field data in the middle?
This is the pitch angle, distribution of the,
Oh, pitch angle.
yeah, of the two telescopes. So it just says this low and short field are not affected by the change of the pitch angle. Yes, okay. So finally, let's have a quick look at the CME drivers. So as for these four SEPs, using like observations in multiple wavelengths, like the type 3 radio burst, UV observation, and white light chronographs, we found that all the CMEs are very narrow, quite narrow and slow, and they are tiny eruptions. They're just tiny eruptions. So together, we can say, or we can try to say that pseudoparticle populations or pseudoparticles can be continuously generated by eruptions or slow and narrow CME eruptions, and they can spread over a large part of the heliosphere, and they can remain there for tens of hours, even if the minimal particle intensity enhancement are measured near 1 stereo, for example. So this is just one, like this is one event using like even close to the sun environment and using advanced observation techniques. And again, using those observational techniques, we can do more. For example, like we can study the relationship between the extreme ultraviolet waves and the particle release and acceleration. Here, this two movies shows the UV waves propagating on the solar surface like this. This is a limb view, and UV waves are thought to be the footprint on the solar surface of the coronal shock, of the CME-driven shock, and we would like to study how this UV wave is related to this particle release and acceleration. And we focus on this event in 2021. And this event was observed by 4 spacecraft at 4 different locations, at Solar Orbiter, at Park Solar Probe, at Stereo A here, and at L1 point. And we, based on this in situ measurement, we can estimate the particle release time. So it means that when the particles are released in the corona regarding these 4 spacecraft. And then we can also measure or estimate when the time when this UV wave connects to these 4 points of these 4 spacecraft. So in a traditional scenario, that they thought that if the UV wave connects to the footpoints, then the particles are found to be released immediately when this UV wave connects to the footpoints. However, when we compare like these 2 times, we found that the particle release time here are delayed by 30 to 60 minutes, like, which is quite significant compared to the time when the UV wave passing through the spacecraft. So this is different from previous like traditional scenario. Then we wanted to know what's the reason of this such a large delay. With that, then we can just say the shock property evolution would be a good indicator to answer this question. And to do this, first we need the shock. We need to know the shock properties. We use the shock geometric model to reconstruct the shock 3D morphology based on multiple viewpoints observations. And with this model, we can get the shock parameters, like the height, like the shock speed, as shown here. And you can see that the shock is experience and acceleration during the shock propagating outward. And with that shock information, we then need to know the solar wind background information because we need to know the shock strength, then we need the background information. And with that, in situ measurement, like here, we can get the variation of the background magnetic field strength, number density, and also the solar wind speed from the low coronal to interface phase. And then with these two magnetic field and number density, we can get the variation of the background ultimate speed. It should increasing and then decreasing. So combining the previous shock parameters, we can get the variation of the shock strength, the Mach number as shown here. So it's increasing during shock propagating outside. And then during the particle release time, the Mach number is found to be around 1.4. So how to explain this 1.4 if we see the particle spectrum at the first stage part, and if we focus on higher energies like this here and here, and we found that at the first stage part, the spectral indices are found to be all around 3. And based on like the diffuse shock acceleration mechanism, it will predict shock Mach number to be around 1.4 if the spectral indices are around 3. So this 1.4 is quite consistent with what we found here with the during the particle release time in the high coronal. So it's explained that the release time of SEPs is consistent with the time when the shock strength becomes stronger enough to efficiently accelerate particles and finally make the release of those particles. So let's have a summary here. This is what we can do use like advanced observational techniques, and we can do more of these particle studies. But here, as we start the particle SEP studies and the four SEP studies, and then we will jump to the second chapter, CME studies. So then we jump to the second part called mass ejections. Since I am at the CME group, as just introduced, and working with NOI, we must have many CME projects, of course. And coronal mass ejections, of course, they are one of my favorite research topics, and the other one is particles. So here that at large scale eruption in the solar system, CMEs are very important. And here we focus on one point, the expansion in the radial direction. So how to understand this radial expansion? The radial expansion can be understood by the increase of the size of the CME cross section along this radial direction, as shown like here. And then there are a fundamental property of CMEs. They can affect the CME space-wide effect by increase the CME radial size and then decrease the CME internal magnetic field strength because their magnetic field strength is important for the geomagnetic storms. And then they can help better understand the CME eruption and propagation. And to study the CME radial expansion, we can use, of course, remote sensing images to measure the morphology trend of the CME cross section here. And then we can also use in situ measurements as shown like this. And as single spacecraft, the velocity decrease here just indicates the existence of the radial expansion. And this is just one single spacecraft measurement. And if we have multiple spacecraft measurements, especially when those spacecraft are in a good radial alignment, then we can estimate the CME, like the decrease of the CME magnetic field strength when the CME pass through two spacecraft like this. Then it will have better understanding the CME radial expansion, like from multiple radial aligned in situ measurements. And then using a similar technique, the CME radial expansion mechanism is found to be different when the CME is close to the sun in this region due to the CME internal pressure. And when the CME is propagating further away from the sun, the mechanism is different, but due to the decrease in the solar wind background pressure. And to like this, but this study is based on in situ measurements. And to know more and to know the CME evolution, we also need to like combine, of course, remote sensing images. And then we need to continuously check CMEs from the low coronal to interplanetary space. And this is one case showing the CME can be continually check by remote sensing images and the two in situ spacecraft like here and here. When the CME is propagating along this line, it will pass through these two spacecraft as detected here. And then we select like 20 single CME such events observed remotely and observed by radio aligned spacecraft, at least two radio aligned spacecraft. And then we study for example, we study evolution of the radio size from the low corona to interface space using remote sensing images and using two in situ measurements. If we compare the radio size evolution between remote and in situ estimations, we can find that the remote estimations can be consistent, like here, with two or one unknown spacecraft in situ measurements. So this is and then we study radio size differences between the remote and in situ measurements of this total 22 events, as shown here, at different heliocentric distances. As you can see, like if we focus on this one, the radio size difference will become smaller when the CME is close to the sun. So it would, for example, it would indicate that the CME expansion mechanism would be different. Like when the CME goes upward, it may indicate the identification of the CME like boundaries. So with this, we can have a summary of this like CME expansion study. We use both remote sensing and in situ measurements from multiple spacecraft at different locations to study the CME radio expansion. And this is important because like now we can continuously track the CME outflow. But for those like as previous slide shows, for those inconsistencies, one reason is that in both remote sensing images and of course in situ measurements, sometimes it's very hard to identify the CME railhead or like the structural boundaries as shown by these two figures. Like here, you can, for this one, you can easily identify where the CME boundary is, but for this one, it's diffuse and hard to find where the CME. So in order to solve this one, we would like to say if we can have simultaneous, for example, we can have simultaneous remote sensing images and in situ measurements together, then it will have better understanding the CME substructure because remote sensing images only have density information. If we can have magnetic field like temperature, then it will help more. So there are two-part studies showing the simultaneous observations, remote and in situ observations, like study the remote sensing images in situ measurement, remote sensing image and in situ measurements. They compare the CME signatures of the remote cavity, the magnetic cloud region, these two bright groups, and the density enhancement ahead and behind the CME. But for these two studies and also other past studies, the in situ measurements are only limited near 1 year because they don't have measurements close to the sun, and also combining remote sensing image together. And these images, they just do a direct image comparison. They don't have quantitative analysis. So with this, we can ask ourselves that can we quantitatively link the CME substructure and also the radio expansion when the CME is in the innermost hemisphere? And at this time, we want plasma measurement or plasma parameters. Our class study is not available because we use those planetary regions. They only have magnetic field information without plasma measurement. So it's not possible for the previous study. And here comes with this requirement. Here comes our solar orbiter event. So thanks to the launch of solar orbiter carrying solar wind plasma measurements, we can check, like for example, one CME from the very low corona, like to high corona and to interplanetary space using UV images, white light chromographs, and heliospheric images like this. And during this time, solar orbiter was at around 0.4 AU, and it also detects the passing of this CME, contains the short stream and ejector regions. And at solar orbiter measurement, one thing I would like to emphasize is that the enhancement behind this CME. So how can we use this? How can we use this for the CME boundary identification? Let's do a image comparison first. So let's see the left hand left part, this is a GMAP. How to understand the GMAP? GMAP means that the x-axis is the time and the y is the distance. So it is a time distance array along a fixed angle. So it is good to show the evolution, temporal evolution of an outward moving transient, like by this bright route and also this dark cavity region. So if we overplot the suboptimal boundaries here and we compare this white, these dark cavity regions, we can first see that, of course, the CME substructures in remote sensing images are generally consistent with those measured in situ, and also the density enhancement measured at orbit and measured remotely, they are consistent. So they can indicate the signature used to better identify the CME trailing edge. And then, as we said before, we need a quantitative measurement. So we estimate the evolution of the radial size, the propagation speed, and the expansion speed of different CME substructures based on remote sensing images, based on this GMAP, different substructure, and also based on in situ measurements at the orbit shown by these pink squares. And overall, we found that these parameters are estimated remotely are quite consistent with the in situ measurement that show like this for the whole CME structure, but not for the magnetic jack part. This is further investigation, and this is one point we'd like to do in our future research. And for this, let's have a quick summary. Here is that we are now using solar optic in the most hemisphere to study CME structure evolution, to study CME expansion. It is helpful with plasma measurement, and it's also helpful when we have solar optic, we have a solar probe in the most hemisphere, and then we can do more. So with this CME experience and the background, we are now in the third part of the future research plans. This research plans is about CME study using observations, and now we also use numerical simulations. It includes 5 proposals and grants, including 2 funded, in which I serve as PI, and 3 submitted, in which I serve as co-I. So we will quickly go through them, like these 5 research directions. And the first is about the comprehensive analysis of the 3-part structure of CMEs. As for CME studies, I have talked a lot about the CME substructures, the CME sheet, the CME ejector part, but we don't, that structure are still under debate. We don't know how they are linked back to the sun. And as for this CME eruptive structure, they sometimes can be very complicated, and they involve many interesting physics inside. And as for the CME 3-part structure, in white light image here, it contains a bright leading edge, bright front, a dark cavity here, and a following bright core. And during the CME eruption processes, this 3-part structure may be related to different eruption materials, eruption structures, for example, shown like this EOB, in this EOB wavelengths. So inspired by this scenario and by our past CME expansion studies, we can ask 3 scientific questions here. That's how we want to study the CME 3-part structure, how we want to start, why we want to study the CME trailing edge, and how to link remote and in situ measurements. And to solve these 3 questions, we use remote observations from the low Coronal to high Coronal in multiple wavelengths, and then we use in situ measurements here in the most hemisphere, and then we also use MSD numerical simulations that I have done previously, but I will reuse code. And as for the second study, it is about the harmonic fluctuation inside ICMEs, and this graph was submitted by Dr. Camilla Scully and then transferred to me now. So this study is about the investigations of the CME ability to respond to external perturbations in a coherent manner, and the role of harmonic fluctuations as the mediators from local to global scales. how to understand coherence of CMEs. It can be indicated by that the information propagation speed inside the CME, for example, the action speed, should be faster than the geometric speed of the CME, for example, the expansion speed. And if the expansion speed is higher, like in this region, it means the same structure is not coherent or is incoherent. Then the CMEs can have different coherence scales as shown here. And different coherence scales will lead to different behaviors of CMEs response to the outer perturbations. So we need to know these coherence after fluctuations. And for this, we also have three standard questions. And inside that, outer fluctuations are the most important thing. And it is important in solar wave, and of course in column-mass frictions, especially when CMEs are low Platzl beta structure. And then we use in situ measurement, we primarily use in situ measurement form at different locations to solve these three standard questions. And then this is the funded one. We are going to propose submitted one. This one is involves collaboration with people from NMC and LAMO. And this is about understanding evolution of CMEs from Coronal interface space, including acceleration, deceleration, expansion, and also the evolution of complexity and coherence. So, but we are now using numerical simulations, and they are in 3D space. And one important thing here is that those CMEs, like here, the fluctuations are inserted in a turbulent solar wind background. So it provides like a more realistic condition for the CME propagation and evolution. So we want to do more about this and use this simulation. And then the final two involves collaboration with Noi, Nana, and Tony. And then the final two are a combination of studying the CME driven sheath region and its comprehensive understanding the formation and development of the CME driven sheath during the CME propagation and the result properties of the sheath region as well as the size of CMEs. We have like 5 standard questions here based on these two plans, and then we will use like high resolution helioscopic images, for example, solo high here in situ measurement from multiple spacecraft, which I have shown previously. And of course, one more is the heavy ion sense of onboard solar orbiter as shown here, and image simulations. And these three proposed one and 2 previous funded one will guide my future CME studies. So with all information, let me make a final outcome summary here. Again, I joined UH since 2019 at September, since I got my PhD in same year. And I did learn a lot with help and support from Noi, from all collaborators, all faculties, friends, and the family. And I learned like a lot, including experiences, publications, and grants, presentation at conferences, seminars, and also help with mentoring postdocs and PhD students, paper reviewing, and of course more. It's hard to use a short time to explain those more things. So finally, really looking forward to the future adventure at UNH Space Science Center. Thank you.
Are we moving to that building?
Yeah, and
God, no. Definitely not. We don't want to be in there with the illustrators.
I have a question, go back to, topic 1.3, so when you talked about the, Mach number at which the particles were released, what is the physics that controls the peak Mach number at which the particles escape into space?
yeah, I think that's a very long, big topic. It's related to first. I think it's related to when the particles are released, when the shock is still accelerating that particles. So you know that the particles are dropped behind and like bang bang. And then it's hard to know when the particles are released. So as for this one, it just, for example, as for this one, you can just find that first the shock is not strong enough, even like the Mach number is still like above 1. but still not strong enough to make efficient particle acceleration, then the particles may be hard to release, like from the chamber of the shot. But maybe after one point, I'm not sure the specific value right now, but as for this case, it is around 1.4. Maybe the shock is not strong enough initially, but becomes stronger. So at that point, the particles is able to be released. So going back to your question, I think it's a big topic, and this is one of my, I would like to do it using like numerical simulation and also using interpretation in the future. That's one, yeah.
I was just surprised, like, if the Mach number keeps getting higher,
It
you
won't,
would think that the.
it won't getting, let me go back. It will become like quite flat afterward, so it won't become extremely higher because first you can see the shock, the speed is almost constant.
Although the
Yeah, after
thermal speed,
yeah,
the thermal speed drops, the thermal, so the Mach number goes up even if the speed is.
Yeah.
constant.
but the thing is that is still decrease, the similarly is still decreasing during the propagation, and but it's still hard to know whether the shock will propagate freely or still attached to the driver. So if the shock is still attached to the driver, then the decreased speed will still cause like the decrease in the shock strength. So right now it's, yeah, it is still under debate that when the particles will be released.
The acceleration of the particles and the release of the particles are two different things.
Yes, yes,
And the release of the particles kind of depends upon what the upstream turbulence
yes.
is. And may not have any strong relationship to the, well, once you get it sufficiently fast, you know,
Yeah.
I mean, there may not be much of a relationship, you know, with, with the LP Mach number after that.
Yeah, that's just, like the particles getting accelerated, and then when it is like getting released, it's still hard to know now. And some, and I think in my memory, some analytical studies found that as for like strong CMEs, the time between the acceleration and release is like around 20 minutes. And but this is still need further investigation of the time of the particle release and acceleration. And also, of course, the release depends on the upstream condition, like the, for example, like I think the shock normal is one important factor.
Yes. I mean, the delays typically for GLEs,
Yeah, but this is not a,
no, I know,
yeah,
10, 20 minutes.
yeah,
You know, because obviously, you know, considerable acceleration taking place before that, and then they break out.
So, to explore those particle questions, you may be curious that why in the future research plans, I only have CME studies. So, of course, I want to do particles, but that grant requires me to contribute my time to CME, but I do expect some collaborations with people, with NOI and with our SSC faculties. And I do have some collaborations with Zhuang from Dartmouth College, and continued collaboration with David Larry from NASA, and Dr. Wei and Huang from UC Berkeley. And for that particle acceleration and release with Zhuang, we can use numerical simulations using the PIS simulations to study the seed particle population associated with flares. And then this may be useful if we also insert a shock behind. This may be useful to further dig into that acceleration and release issue. So
I was gonna ask you if you're gonna do all this yourself.
yeah, but this is one point. Yeah, outside of range, but still could be in the future. So, yeah.
Oh, magnetic connectivity, I understand as a footprint to the spacecraft, how magnetic field is connected. How do you characterize like good magnetic connectivity?
Simple way is that you track the normal Park spiral back to the sun. So the normal Park spiral can be easily calculated based on solar wind speed and also the solar rotation speed. So if you track the normal Park spiral back to the sun, and then you know the location of that trip point, and you know the location of the active region of the same SEP subregion, then we will know how large the separation between these two.
So, okay,
Cost.
so the actual measurement of magnetic field and the predicted by the Parker solar.
This is what the easiest way is that, and then a more complicated way is that you use Park spiral combining the coronal field, magnetic field extrapolation. So there are many ways to do this.
So near the beginning of the presentation, you were talking about all the different factors that lead to like observation of
Yeah.
large SEP fluxes.
Mhm.
And one of those many criteria was that a CME is fast and wide. Can you elaborate on the wide criterion, and why does a wide CME increase the flux you would observe at a single point?
In principle, that there's a relationship that this semi is a higher speed should be
Right.
much wide because you want a strong eruption.
So just more energetic event.
Yeah.
Is that?
Yeah, and that strong eruption will involve everything.
So you would never see a fast but narrow CME or a wide but slow CME.
Why slow semi? It's really hard to see that.
Right, yeah,
Yeah. Okay. No, no.
thanks.
Especially very slow semi is extremely wide.
The diffusive shock acceleration is like it predicted around the same point, the delay time, according to the data. Does it? There is like a theoretical prediction, there's like a formula, and then like.
Yes, so if you go back to this paper, there are lots of formulas. And then you take the final one, that's the relationship between the shock Mach number and the energy spectrum. Then you get the final one, and then you can easily get the how the prediction of the number based on this energy spectrum.
Any other question? Yeah. Right, let's